Hi everyone, my name is Dominic Orchard and welcome to a lightning quick review of the Granule project in 2020. I thought this would be a great opportunity to talk about what we've been doing this year and also to show you the features in the latest version of the Granule programming language. So this is a joint research project between the University of Kent, myself, and my collaborator Harley Eads at Augusta University. Now, just to introduce you to the rest of the team, this year we've had Michael Vollmer join us as a postdoc, and we also have a number of excellent PhD students on the project: Aubrey Bryant, Jack Hughes, Willem Leopelt, Daniel Marshall, who's new this year, and Benjamin Moon. And formally next year we have Tori Vollmer also joining us as a research assistant. We've been really lucky this year to have a number of fantastic undergraduate students also working with us: Declan Barnes, James Dyer, Rowan Smith, and Jake Chewton. So in this short video, I'm mostly going to be in the first part showing you some of the new features that are in version 0.8 of Granule, which has just been released. I'm also then going to go over some of the results that we've published this year and some of the things that are coming out early in 2021. You can find all of the papers I'm mentioning and more details over at the Granule project website. If you don't know much about the Granule project or the language, then I'd encourage you to take a look at some previous talks. A good starting point would be Willem's ICFP talk from last year. That gives a nice short condensed introduction to the language, the ideas, the core theories. If you're looking for something a little bit more tutorial-like, then my CodeMesh talk from last year goes through some key ideas in the Granule language and demos lots of code. You can download the Granule language from the GitHub that's linked here. As I said, we've got version 0.8 just recently released, which you can find here. There's some binaries. You might also want to build it from source. There are instructions for doing that over here on the GitHub. You'll need the stack build system of Haskell to do that. You'll also need to install Z3. You can find more details here. You can also find linked the Visual Studio Code extension, which I'm going to be using today, which smooths things interaction with the Granule tool. So over to code. So a big thing that we've been working on this year is program synthesis, generating programs automatically based on types, using the linear and graded types in Granule to direct that proof search. So I'm going to give you a little demo of that now. Let's stick in the good old either type that we know and love, familiar to Haskell programmers, and let's consider eliminating an either. So we've got an either AB, we've got a function that goes A to C, another function that goes B to C, and we want to use both of these to eliminate this. So if we have a left, we'll use this function to turn the A into a C, but if this is a right, we'll use this function to turn the B into a C, and we get C out. So add that to the quantification here. So I'm going to load this up so far into the REPL. This checks everything there, but we've got a hole. We can inspect the hole. Tells us what we're expecting here. Okay, we haven't filled in anything yet, so it's just this type. Now, on its own, this type is not actually inhabited in Granule because the base system is linear, and these two functions here, depending on this value, one of them will be used and not the other. So we need to mark that in the type system using the graded modalities. So I can do that here and say that each one of these functions is used 0 or 1 times, so 0 to 1 times. Okay, so we're now in a position for Granule to automatically generate this program for us. So I'm going to put my cursor here and I'm going to press Ctrl EE in Visual Studio Code, and it's automatically generated that for us. Let's do another simple program. I'm going to write the copy program, takes an A that you can use twice and turns it into a pair of A's. So the synthesized program takes this graded modal A that has the capability for usage twice, it unboxes it, and now we can use that capability in the body of the function. So indeed, everything here, type checks. So one of the things we've been doing this year is that we've been making various parts of the Granule type system a little bit more general, as well as the synthesis work. So one thing we can do here is, rather than just saying 2, which means exactly 2 uses, we can quantify over any semi-ring and replace this with 1 plus 1 of type S. So I can also synthesize in this context the same program. The 1 of the semi-ring counts a usage here, and 1 plus 1 means then that we have 2 subterms, each using this resource once. So this is a general term in any semi-ring, and therefore this program is parametric in the semi-ring graded modality. So we can use this quite generally, and our synthesis procedure works in this context. So our program synthesis work was published at the Lopstra conference, Lopstra 2020, in this paper entitled Resourceful Program Synthesis from Graded Linear Types. That's with my student Jack. And what we did was we looked in the literature. In the 90s, there was a bunch of work looking at doing proof search for linear logic, and we take that and extend it to the graded setting. Now it becomes quite interesting to think about how you manage the grades and essentially how you manage resources as you do the program synthesis search. And in the paper we propose there's 2 approaches to doing this, what we call the subtractive or the additive approach, which are different modes of accounting for the resources as you generate programs and as you search the space. And so we prove various theoretical things about this, and then we also do a quantitative analysis on the speed of these 2 approaches to look at what has the best performance for automatically generating programs. And that's all implemented in the Granule programming language, as you've just seen. And this was, this work went really well. Jack worked really hard, and it also won Best Paper Award, which is great. Another related thing we've been doing then is we have a system in Granule now for also automatically deriving combinators, not using the program synthesis approach, but using more of like a generic programming calculational approach. So this is something that Jack and Mike and myself have been doing, and this idea kind of started a little while ago. We noticed that when programming with Granule, you sometimes ended up in a situation where the graded modalities were kind of in the wrong place. So maybe you had in your in some code that you were writing, what you wanted was to have a list of A's, say, with the graded modality on the outside, so a box R of list of A's. But what you actually had in your hand was a list of boxed A's, so the modality was sort of inside rather than on the outside. So then what you need is what's called a distributive law, which is going to interface these 2 bits of code. So a pull distributive law in this setting would be taking some value of a data type F, say lists, with boxed A on the inside, and we want to pull out that box onto the outside to get box F of A. And dually, a push distributive law would be pushing the modality on the inside, a box FA, turning that into an F box A. And of course, we also want to do this in a graded setting, not just in a regular modal setting. So it turns out you can do this automatically. You can automatically compute and derive these distributive laws for these data types F. And we detail this idea in this paper, Deriving Distributive Laws for Graded Linear Types. Jack presented a version of this at the TLLA Linearity Workshop earlier in the year. And then with Mike, we took this a little bit further, provided more details. And also, I think even more interestingly, is we applied this to linear Haskell as well. So this isn't just a Granule specific thing. If you've been following along with the linear Haskell developments, so in GHC9, there's going to be the linear types extension available to you. And the way that linear types work in this extension for Haskell is based on a graded system. It's based on a graded type system to track linear usage or non-linear usage. And so you can work with graded modalities in this new version of GHC as well, which is really nice. And so we show how you can apply this technique there as well. We compare Granule with linear Haskell. We also compare with some other recent work in the literature and use it as a way of studying these different type systems in more detail. So how does this look in Granule? Let's actually see the code again. So one of the simplest kinds of distributive law we could do is for pairs. So let's say we take a pair whose components have a graded modality. Let's do this for all graded modalities, so all semirings S and all elements of that R. And we want to pull out this graded modality onto the outside. So this is actually something that we could just synthesize. It works by unboxing each of the parts of the pair and then reboxing with the pair on the inside. So we could do that. Alternatively, we can use this new deriving mechanism inside of Granule. So we can write pull. This is a generic combinator, and write a type application and say we want this combinator applied to pairs. And this will then, inside of Granule, it will automatically generate this distributive law for us. Now this becomes extra nice then once we're working with our own data types. So let's say we've got the good old GADT of sized vectors, and we're then working with a bit of code where we want to do a push on this. So we've got some vector of length n, element type A, and it's got a graded modality around it. Okay, so I need to do this generally. And I want to then push that in, let's say, to get a vector of length n whose elements are graded instead. So this is a push. So we can write this, instead of having to write it ourselves, we can have this boilerplate automatically generated for us. Now, this is actually going to produce a type error coming from the grades. It says that R is less than or equal to this unification variable R0, and R0 is less than or equal to R, so they're the same. We're saying R equals R0 here. And this constraint here says that 1 has to be less than R. This means that R has to over approximate 1, and 1 counts usage and inspection of the data. So why is that? Well, it comes down to how Granule gives a typed analysis to pattern matching. In order to traverse this entire data type, we need to pattern match on its constructors. That means we actually have to consume them. We have to observe or inspect them as we go. So this pattern matching induces a usage of 1. So this R can't be 0. That's what this constraint is saying. We have to say that we have this constraint generated here, which says, well, it has to accommodate at least 1 usage. And that's represented by this pre-ordering here that's related to this semiring. So I have to represent that constraint generally here, and then, assuming I didn't make any typos, okay, then that's well typed. So this relates to the typed analysis of pattern matching, as I said, and in our paper, we go into more detail about that and compare this idea with other recent systems like the ICFP paper of Abel and Bernardi, ICFP 2020, the grad system, which is going to be at Popple, and Granule and linear Haskell. So if you're interested in that kind of the co-effect semantics of pattern matching or graded semantics of pattern matching, we've got a lot of detail there. But generally, this gives us a facility for automatically deriving useful combinators for programming in this graded setting. And we also have, we can also automatically derive copy and drop functions as well. But to keep things short, I won't go into that as well. Let's think. So just one last thing that got added in this new version of Granule is we can do type level case, which is kind of useful. This is a different kind of feature, but it's for giving us a little bit of extra type level computation. So say I'm looking at doing a head on a vector like this. Obviously this operation is only defined if n is greater than 1. So I could do n+1 like this. I could define a safe head like that. Another thing I could do here is I could actually track, keep the n in there, but I could write a case statement at the type level now, which says, well, if n is 0, then we have unit type. Otherwise, we can do a like this. So then I can, I'm going to use the case splitting feature, which is part of the program synthesis suite. I'm going to stick just some extra names in here to help the naming look good. So I'm just adding in some default names into the data type here. It looks a bit like a dependent function type. And let's, you know what, I just remember that this will need to be modal as well, because I'm going to have to throw away the tail. Okay, so in the nil case, okay, I don't have any head to return, so I'm just going to do empty type. And in the cons case, I get just the head. And it's wrapped in a modality because we need to throw away the tail here as well. So that just shows off this type level case expression that we can use here. This is also useful when you're working with session types in Granule, because you can then use it to direct the behavior of your types based on the values. So this was implemented by James Dyer, one of the undergraduate students who was working on this and other bits of the Granule language this year. Now, of course, yes, we could write safe head in various other ways. Just quickly, another way is that we could have said, we could have done n+1, or we could have said that n has to be greater than 1, and things like that, using a kind of refinement type. So we could also do that. There are lots of different ways of doing these things, but yeah, there you go. Okay, so I think that's all I want to show about Granule version 0.8. Do go online and have a play, download it, let us know if you find any bugs. It's active development. We actually have a new version in the works already. We've got lots of new things coming along on different branches, and new graded modalities, new semi-rings, new language features, and so on. And thanks also to Declan Barnes, who worked on this case splitting feature with graded types over the last year. Right, so that's the look into what we've been up to with the Granule language. I'm now going to dive into just some of the other results and papers that we've been working on this year. So the Granule project encompasses both practice and theory. So there's a bunch of interesting theory we've been doing this year. So with myself, Harley and Phil Wadler, we published a paper at MSFP 2020. That's mathematically structured functional programming. And in that paper, we looked at graded monads and parameterized monads. These are two indexed generalizations of monads that appear in the literature, which kind of seem to have some similarity. If you squint, they kind of look a bit similar. There's applications of these two structures which overlap. So we asked the question, in what way are they related? What's the relative expressive power of graded and parameterized monads? And we studied this question through the lens of category theory and through the lens of lax functors. So there's an old result from the 1960s that says a monad can be viewed as a lax functor, mapping from the single object singleton category 1 to the single object category of endofunctors on C. So it has lots of morphisms, and those morphisms are the endofunctors. So this is a kind of well-known view of monads as a lax functor. And then to this we can apply a generalization tactic from the literature, which is called oidification, or alternatively it's called horizontal categorification. Both beautiful phrases. And what this means is to stare at your category theory definition, find something that involves a single object category, and generalize that to any category, to any multi-object category. So we can do that in the source category here, and what we end up with is this structure which looks a lot like a graded monad, but instead of being graded by a monoid, we're now graded by a category. We're graded by the morphisms of that category. So the unit operation is indexed by identities, and the join operation has grades which are morphisms F and G, and then it gives their composition in the result. So we call this a category graded monad because it's analogous to a monoid graded monad, but now we're grading by categories. And in the paper we show that this captures a subset of graded monads and parameterized monads in the literature, and then with a little bit of extra generalization we can capture the full structures. So we use this as a way of exploring their relative expressive power and actually coming up with a top point which unifies both of the approaches. So some of this is based on observations that have been around for a little while, and we just explore this in detail in the paper. Another thing that I was doing this year with colleagues at the University of Cambridge, with Andrei Vaskovich and Alan Mycroft, is that we've been looking at the application of graded monads in the semantics of side effects and imperative programming. So in this paper we compare data flow analyses, classical static analysis kind of ideas, with effect systems and graded monads. These effect systems are kind of a general paradigm of doing particular kinds of static analysis for functional programs. Monotone data flow analysis is like a general paradigm of doing data flow analyses over control flow graphs. And they're both these general classes of analysis. And in the past, I wondered, could they be related in some way? Because in the early days when we were doing co-effect system work, we discovered that you could represent a live variable style analysis as a co-effect system. So it started us thinking, well, could we relate other kinds of data flow analysis to effect systems or co-effect system ideas? Well, in this paper, what we do is we show that, well, on this effect system side, this is a sort of well-established idea that you can take effect systems and you can give them a semantics in terms of a graded monad. So the effect system tracks that you have some side effects F for your program, and when you interpret this as a morphism, use a graded monad MF, where that F information can then be used to specialize the semantics, to refine the semantics based on the information about what effects can be done here. So in the paper we show that you can give you can characterize monotone data flow analysis in such a way over control flow graphs that they can then be translated over into a graded monadic semantics by just following McCarthy's translation from imperative programs into functional programs. So we take this classic transformation, but we map to a graded monad space. So this we show that this gives us a sound way to transport across classic data flow analysis into this functional world and map these classic data flow analyses down onto the grades of a graded monad. We then pick a particular analysis, in this case live variable analysis, and show that we can give a graded monad which takes the information of a live variable analysis and really refines the semantics down. And this gives us a way of proving the correctness of the live variable analysis, essentially for free via kind of a semantic technique. And then in the future, we hope this provides a way for doing things like verified optimizing compilers, verifying that dead code analysis is sound, but getting that proof essentially for free by the structure of the graded semantics. So we're really starting to push on using graded monads to get extra power here in our semantic definitions. And you can go and check out the paper linked from the project website. So that's mostly it that I want to say about 2020. We've got a few things that are on the horizon for 2021, which we know are coming out soon, so I thought it'd be a good chance just to mention them to you. So one of the things we've been working on for a while is looking at combining grading with dependent types. So taking the power of grading to track how data is used in your program and extending that to work in the dependent type setting where data can flow between your types and your computations and back again and so on. So there's sort of much richer data flow in that setting. So Harley has a paper that's appearing at POPL 2021 very soon, a graded dependent type system with a usage-aware semantics. And this is with Pritam Chowdhury, Richard Eisenberg and Stephanie Werrick. And there they have a really interesting piece of work, which is it's kind of in on the roadmap towards unifying ideas in linear Haskell with developments in dependently typed Haskell, and looking at how we can use this sort of grading approach to track resource usage in both places and actually help us to implement a dependently typed language that can also do this resource tracking as well. One of the things I really like about this paper is they also have this really nice heap semantic model which lets you reason about resource usage all the way down to the operational level. So keep an eye out for that. And then also in this area, we have a paper appearing at ESOP 2021. This is with my student Ben, so Ben Moon and Harley and myself. What we do here is we take the kind of core idea from graded modal types, and we use grading in a very kind of uniform way to track data usage at all levels, both in the computations and in the types, in a completely uniform way, so there's no real distinction from the grading point of view. So this is like being able to track how much your values are used in the types, and then that lets you characterize different kinds of type system and the data flow that's contained within them. So this is something we've been working on for a little while, so we're really excited for this to come out, so keep an eye out for that. This also comes with a new language, a language implementation called Gertie, which is somewhat a little like the core of Granule, but as I said, it has this full dependent type system with the graded tracking at all levels. So you end up with sort of double grades telling you how is this thing used in the types and how is this thing used in the runtime computations. So we'll be releasing Gertie sometime early in the new year for people to play with. And in a slightly different direction, also appearing at ESOP 2021 is graded Hoare logic and its categorical semantics, which is with my co-authors Marco Gabuardi, Shinya Katsumata, and Tetsuya Sato. This is an interesting thing we've been thinking about for a while. We've noticed in the literature that there are quite a few quantitative versions of Floyd Hoare logics. These are like Hoare logic with other bits of information tracked in a very graded-like way. So we show that the various approaches from the literature can be generalized and captured by a general graded Hoare logic, which tracks information along with its inference rules. And we give a categorical semantics in terms of a general notion of graded Freyd categories. So this is grading back in the imperative in world, but also looking at semantic models and unifying various things from the literature. And lastly, something else we have that's a work in progress is on what we call graded adjoint logic. So Harley presented earlier in the year at the TLLA linearity workshops. He presented the kernel of this idea in our short paper, Grading Adjoint Logic. And in this work, what we do is we take Benton's linear, non-linear mixed logic, and we show that it can be turned into a graded version, which can also then capture ideas from adjoint logic. And we can come up with a very powerful logical system for controlling structural rules. So we're working on that at the moment. That's with Harley, Tori, myself, and Jake. Okay, so that was a whistle-stop tour of what we've been up to. Do check out Granule version 0.8, and you can find all the links and information there online. It's worth saying that it's been a tricky year. 2020 has of course been not very kind to us all. But I'm really thankful for all my students and collaborators and colleagues who've, despite the difficult year, have just still made this really fun. We've really enjoyed ourselves in this research, and it's worth saying as well that all the sort of various papers that have come out this year have been the work of many years that have gone before. And so we've been working on these things for some time. It's just they've happened to come out this year. In this difficult year, but it's been an enjoyable one nonetheless. So I do hope you get to check out Granule and let us know if you have any ideas or would like to collaborate, or do raise issues if you spot any bugs as well. So thank you very much, and thank you also to the UK Engineering and Physical Sciences Research Council for funding some of this work. Cheers.